welcome one more time. This is being our last presentation of the day. For this presentation, we have Moshe Zadka, which they're gonna be talking about tests and classifiers. Now, the reason to write and run tests on the code is to detect bugs before the code is being used for the customer, right? But too often we forgot this purpose, and when deciding what to test, what makes a good test, what makes a good test suite, how can we measure it? By modeling tests as a classifier, where the label is buggy or not buggy, the general theory of classification can be applied. About Moshe, they have been involved in the Linux community since 1998, helping Linux installation parties. They have been programming Python since 1999 and have contributed to the core Python interpreter. Moshe has been a DevOps software reliability engineer way before this term ever existed, caring deeply about software reliability. They have worked in companies as small as 3 people and as big as 10,000, usually some places around where software meets system administration. Thank you very much, Moshe, for being here with us, and the stage is all yours.
Hi, everybody. My name is Moshe Zadka. I work as a principal engineer at Palo Alto Networks in the engineering productivity team, and I'm excited to share some of my thoughts about tests with you. Hi, everybody. My name is Moshe Zadka. My website is cobadism.com, where you can find every way of reaching me known to humankind. And today I want to talk about thinking of tests as classifiers. I want to start with an acknowledgement of country. I live in Belmont in the San Francisco Bay Area Peninsula, which is the ancestral homeland of the Ramaytush Oholoni people. So, what is a classifier? A classifier is something that takes as input something. It doesn't really matter what kind of input it takes. What matters is that the output is true or false. It's classifying whether it's there or not, whether it belongs to a set or does not belong to a set. So let's give an example of a classifier. If you've ever Googled chihuahua or muffin, the input is an image, a set of pixels representing a chihuahua or a muffin. And the output is whether it's a chihuahua dog. It's kind of funny, it's amusing, but it is a good example of like what is a classifier, right? And before we go think about how to treat tested classifiers, let's dive in more about thinking about how classifiers work from the inside a bit. So classifiers can fail, right? They can have something that, there's like different definitions. It can be a false positive or a type 1 error. I like to call it a false alarm because that's much harder to mistake. When the classifier says yes, right, it's alarming. It say, hey, you should file this as a dog. And it should say no, right? So if you give an image recognition system a picture of a muffin and the classifier says it's a dog, then this is a false alarm. Right? This means that a classifier failed by saying it's a dog when it shouldn't say that. The other kind of failure a classifier can have is that it says no and it should say yes, right? It tells you, you don't have to save this in the dog pile, but it should, right? It's missing it, right? So the example is, in this case, if they give you a picture of a dog and the classifier says it's not a dog, it's a muffin, right? And I want those things, this is like the simplest case of a classifier, and this is really important to kind of keep remembering that this is how classifiers work. The reason is because now we're going to start thinking about test suites as classifiers. So a single test is not what classifies the code, right? What classifies the code is you give it a code change, the CI system, right? You can think of the whole CI systems, but I'm going to focus on the test part. And that CI system runs the unit tests, and if a single unit test fails, the code is buggy, right? It's a classifier, right? That code change, that code diff belongs to the buggy pile, right? It's alarming on that. And if it's not buggy, then it's good, right? And if you think about it in that way, right, like test suite failure means this code change is buggy, and when the test suite succeeds, it says code not buggy. I want to specifically think of the classifier going this way, right, where it fails, it raises the alarm, and it succeeds. It doesn't raise the alarm because that's gonna make a lot more of the definitions in the following steps make a lot more sense. So here are a few examples of the simple classifiers, right? Again, it doesn't matter. We can do that in the chihuahua or muffin, right? We can have the thing that makes sure that you'll never miss a picture of a dog is to always say, it's probably a dog. That's really easy, right? You can probably write this function yourself, right? Like def, is it a dog of set of pixels? Return true. If you're very low on resources, right, for saving pictures of dogs, right, you can also have the classifier that says never alarm. Same source code except return false, right? That's returns, that's regardless of input, it never alarms. The reason these are important is because, as I said, these are really easy to write. The only reason to write a better classifier is if we can somehow say in what sense is it better. But you probably have some intuitive sense that this is a pretty bad image recognition system, right? If it always says it's a dog or it always says it's a chihuahua. And in that sense, we can use the same intuition to say this is probably a bad unit test suite, right? This is a test suite that will never let buggy code be merged, right? This is great, right? Like you check it in and you know for sure that no one can check in buggy code. That's very easy to write. I just wrote it. You can probably copy it and paste it off the slide. Two lines, you're done, right? You can also, write a test suite that's even easier, that never alarms, right? You don't even have to write a succeeding test. All you need to do is check in an empty file, and you're done, right? That's the, if you want to think about the Volkswagen tests, right? And these are very easy to write, again. So when we model tests as classifiers, we need to have some measurement that says, why should I invest more time than this? Right? There's probably a reason, right? And intuitively, probably, write tests for some reason. But let's think about exactly how we model that reason. So writing tests is really hard work, right? I'm sure if sometimes how much we have to argue about how much time we allocate for tests, it's a lot of work. A lot of work should give value, right? And by definition, tests do not run in production. They do not give features, right? So how can we quantify the value that a test gives? And this is where thinking of tests as classifiers is really useful, because there are well understood ways to measure the value of classifiers. So one metric is precision. And precision rewards not alarming when you shouldn't. So that's dividing the true alarms by the true alarms plus false alarms. You might want to add a +1 to make sure that you don't have a divide by 0 error. But anyway, the precision will be, if you kind of add true alarms +1 to true alarms +1, you add +1 all around just to make sure it doesn't get divided by 0 error, you get really high precision if you have 0 false alarms, right? So this is great, right? This is amazing. This is the best classifier ever. It's very precise. But, that would not be a good measurement of, intuitively, right? Wouldn't be a good measurement of, classifier, because then how can you justify working more than 0 minutes on tests? The other measurement is recall. Recall rewards alarming. So it divides true alarms by true alarms plus missing alarms, which means you want to have as few as possible missing alarms compared to the true alarms. Again, you probably want to do some weird thing to avoid dividing by 0. But again, if you always alarm, then you're going to have really great really great rates, right? So this is great. Again, like not obvious why this would be a good measurement, because again, why wouldn't you just write the always failing tests, right? So we need to somehow balance precision and recall, right, to have a good measurement of tests that justifies the values they give us. And that's the F-score. The F-score is a balance of precision and recall. There's a bunch of other ways to vary, but this is like one of the most popular one in actual use by people who write machine learning systems. And this is a really good measurement, right? So it's basically the harmonic mean, right? We take the inverse of the precision, the inverse of the recall, we add them and divide by 2. So we take the mean of the inverses, and then we invert that. That's called the harmonic mean. It has some nice behaviors that are slightly different than the regular mean. There's also like a variation with the geometric mean that's not important right now. But this is a really useful measurement. And one of the useful things about it is it balances exactly precision and recall, right? If you're very precise, which means you never alert when you shouldn't, but you have really bad recall, then you're not going to get a good score, and vice versa. So the F-score will actually, like if you measure that, it will reward writing good tests, right? And it somehow correlates to the notion of good tests. But when I say it balances precisely precision and recall, right? What if it's not equally important? Right? What if you want more recall and less precision, or vice versa? How are you going to reward that? So that's the F beta score. So you see that like it's almost exactly the same as the formula before, but now I have a beta squared multiplying precision invert, and like I divide instead of by 2 by beta squared plus 1, and that means that when beta is 1, F beta is just the F score, and that's why sometimes the F score is so called the F1 score, because it's F1 for beta 1. So that's beta, right? The F score is a beta score, and beta is 1, or sometimes we can just call it the F1 score. And the beta parameter encodes utility, right, or value, right? Like which error hurts harder. And that's a decision you have to make. It depends on what you're delivering, right? If you want to move fast, you're still a small startup, you barely have any users, you're okay, taking a little bit of risk of like not catching bugs if you can deliver features much faster, right? If you're developing a medical device, you probably would prefer to catch all the bugs, and you're okay with an occasional false positive, right? So the utility is in sense of utility theory, right? It's the business value, right? Like you need to know what is the business value of your product for that. And that's a business decision. And this is really important, because this means if people say, oh, we're taking too long to write tests, you say, okay, tell me the beta you want me to get. Tell me how to balance these things. This is important. So, as a rough measurement, right, beta 2 means that missing alarms are twice as painful as false alarms. It means you're very sensitive to bugs, and you're willing to occasionally suffer through, kind of like a unit test that fails without a bug. And the reverse when it's half, right? Missing alarms are half as painful as false alarms. This means you want to move really fast. So these are like, very typical values of beta. Unless you're like in a very extreme circumstances, that's probably the range you want to be in. And by default, F1 is probably going to be reasonably useful. We talked abstractly about classifiers, right? The F score you can apply to any classifier. It doesn't matter if it's tests. But let's think about how tests relate to the F score, right? What qualities of a test or a test suite will bring down the F score. This is important because if you want to keep the F score as high as possible, you want to avoid these things, right? You want to write good tests. That's the notion of a good unit test suite is, does it have a high F score, right? So now we have a measurement of quality that's informed by the business because we let the business choose the beta. So now that we have all this information, let's think about how we can improve the the F score. What kind of features of a test will look good. So There's a few cases of false alarms. One typical false alarm is a flaky test. Right, the flaky test is one that fails randomly. It means even in the presence of no code changes, the flaky test fails. Right, maybe it's a race condition or testing environment, all kinds of things like that. It fails randomly. Right, that will bring down your F-score because it will bring down your precision. All things being the same, precision, lower precision means lower F-score. The other kind of false alarm is what sometimes people call implementation test, right? And that's when your test tests implementation details, which means if you, for example, patch out subprocess check output and run the code, when the code uses subprocess.run instead of subprocess.check output, the unit test will fail, but the code is still valid, right? So this is, we assume too much about the implementation. We made a valid code change, but now the unit has failed, and now we have to modify that, right? That is a cost that lowers the precision and again lowers the F-score. The most typical missing alarms, right? And this is like the easiest thing to test because we have, we understand what code coverage is when the code is literally not executed by the test suite, right? If it's not run, other than like really weird esoteric cases, it doesn't affect the results of the tests. So any bug there is gonna go with the missing alarm. Assuming you've gotten your coverage to where you want it to be, a very much harder thing to measure is loose assertions, right? When you assert that something is greater than 5, but you really should have asserted it's 6, right? Your alert is too loose, right? So this means if there's a bug and this return 5.5 instead of returning 6, you have run the code, you have asserted against the code, right? Loose assertions also covers the kind of, non-assertions, right? If you assert true and you run the code, then this is kind of the ultimately loose assertion. And this also tests something, right? Tests that the code has not raised an exception, but it's still too loose. And that means that bugs in the code are not going to be cut by the unit test suite. So these are the kind of things that can change your F-scores, but how do you know what your F-score is? So if you want to measure the flakiness, you can run the known good main branch a few times, see if any tests fail, and like any tests that fail on a known good main branch are flaky, right? So you can measure the rate that this happens and kind of feed it into the F-score calculation. So this is pretty simple. Measuring implementation tests is kind of harder. You want to measure how many times you had to change tests. But there are cases where you change tests for valid reasons, right? So you want to have some heuristics to compensate for the legitimate changes. This can range all the way from checking the ticket, whether it's a task, or checking if it's just a pure addition to tests, and maybe let people write in the commit message an explanation for why the test would change that kind of helps it determine, right? Kind of ultimately yield to human decisions. The other way to estimate the F-score is to do mutation testing, right? You can do percentage of surviving mutants. That will also lead you to estimate missing alarms, right? So that will help you measure the recall, which is part of measuring the F-score. Another thing is that you can check how many reported bugs cause an extra test. Of course, this is easily gameable by people not writing tests, but ideally, the goal of people is not to mess with your measurement, right? So you can check whether a bug had an added test. That means that this test would have cut the bug, again, assuming that the test would have actually failed on the previous code. And so this is a good thing. But again, you want to make sure that this is a bug and not a new feature. So you still want to do some reasonable heuristics to determine what's what. Again, might check the status of the ticket, or you might want to put in a commit message. And all kinds of variations for like how to actually improve the measurement. So you'll probably have some set of heuristics. You want to weigh things very carefully, right? Because if you have a true alarm, you don't want to give it too much weight. Now, if you have a PR that has a failing test that did catch a bug, you don't want to weigh by how many times people have committed to this PR. So because like until they fix the test, it's still fine. So you probably want to weigh the true alarms by the PR branch. Only count one true alarm per PR or branch. But in that case, it's really important if you can get the data from the dev machines, right? If the test has caught a bug that never made it into the commit or the pushed commit, then you might not see it and you might not count it as a true alarm. So you might underestimate your F-score. So you want to see if you can somehow upload results from test machines into your kind of F-score aggregator thingy. Now, if you measure F-scores in like more or less the way they suggested, it's a very lagging indicator, right? You can only really truly measure it on the code that's already merged. You want to wait until the PR is merged to make sure that you count how many true alarms have been in all of it and not double counting. You want to see, you want to kind of, run main development, which means you only check tests that have already been merged. So that means, you're gonna lag at least a week or two behind, in most realistic cases before you see if you've implemented anything that has actually improved the F-score. So, and that brings us to the point where you want to be careful about how you use the F-score. First of all, as you saw, right, an ideal case of F-score is if which two alarms, how to count all the numbers that come into the calculation. The best we can do in any realistic circumstance is probably have a bunch of heuristics. You probably want to sample the heuristics and check how accurate they are, and kind of give maybe ranges for your F-score, right? So when you know how accurate your heuristics are. So it's not going to be a number. You're going to be able to say my F-score is a range. You also want to make sure to take good hard slow into consideration. As you saw, a lot of these numbers are extremely gameable. If you're gonna, tie it to people's compensation or bonus or things like that, evaluation, you're gonna get them gamed. This is true for pretty much any measurement in software, but I feel it's equally more important to say the more kind of scientific this measurement looks, and F-score is, looks very scientific. You can't tie it to compensation. What you can do is help it guide you in how to improve, in what things you need to work on. And if you do that, this will be extremely valuable to people. But you do not want to make it so that people are incentivized to game the metrics. These are very, very easy metrics to game. One thing that, I always like to think about is revealed preferences, right? If you're not giving enough people time to write unit tests over the long term, that's basically revealed preferences that your beta is much lower than you thought, right? So, basically say, okay, well, that's apparently the beta we care about. Okay, this is gonna be the F-score from now on, right? And if you want to change it, you know that you need to change it. So you can kind of have this back and forth about what should our beta be? How are we, delivering the correct value? It can also help you calibrate the time investment in improving tests. If your F-scores keep dropping down, you know that you're not spending enough on tests, right? If your F-score kind of climbs and stays reasonable, you know that you're probably doing a good job writing tests, and you don't need to focus on that. And you might, be over spending time on it if other metrics are going lower. When you try to improve steps, again, remember that the F-score is a lagging guide. It will tell you whether what you have done over the last 2 weeks kind of was really great, and this is nice, but you can't use it for your day-to-day development. What you want to do is evaluate general strategies with that. But you can improve Flakey tests, for example, by better isolation. As usual, improve implementation tests by having clear contracts, check code coverage, do mutation testing, and to remember, the goal of a unit test is to prevent bugs from creeping into your code, and you want to minimize the cost involved. And you want to decide what is the cost of a bug, and you want to measure what you intended to be, right? Now that you know your goal versus the reality. And then you want to improve. You want to align reality with what you want. And the F-score can be a very useful guide for that. So thank you very much for listening to my talk, and I hope it helped. Goodbye.
Thank you, Moshe, for putting this presentation together and teach us about tests and classifiers.
Thank you, everybody, for listening to the talk, and goodbye.